When you open a shopping app, finding items feels effortless. You tap a filter, drag a slider, and instantly the exact shoes you want appear. But that clean, polished interface is a mask for a much larger complexity. Beneath it lies a database, an endless grid containing millions of unsorted rows of product names, price tags, and vendor codes. Left on its own, this sheer volume of data is unusable. If you had to manually read through every single entry to find a match, the app would be no more efficient than a paper ledger. Every time you touch a slider or check a box, your phone is functioning as a remote control for the database. It translates your intent into back-end commands, specifically the SQL SELECT and WHERE statements. This translation layer is the only reason a user can find a specific item in a mountain of millions of rows, without ever having to write a line of code themselves. Consider a common search. You want shoes priced between $50 and $100. You drag the UI slider to set your budget. The database now has a clear instruction. It must scan the entire inventory and ignore any item that falls outside of that specific financial boundary. The app uses the between operator to define a range where the price falls within the $50 to $100 mark. Establishing these hard numerical boundaries is the foundational step in taking an infinite stack of data and narrowing it down to a manageable subset. But not every search is a number. Sometimes you're looking for a specific vendor, but you aren't sure how to spell the name. Maybe it's Johnson with an O or Johnson with an E. Databases are built on rigid accuracy, but human memory is often partial. If we type in a guess, a standard search might return 0 results because the spelling doesn't match perfectly. SQL bridges this gap with the like operator. By placing an underscore in the middle of John's underscore N, the database is told to treat that spot as a wildcard, accepting any single character that fits the pattern. If you only know the first few letters, this query shows a different approach. The percentage symbol acts as an open-ended wildcard, finding any vendor starting with Smith, regardless of how many letters follow it. These pattern matching tools ensure that a minor typo or a fuzzy memory doesn't prevent the system from finding the correct data point. Now, look at it from the perspective of the database admin. A product page crashes because of a missing supplier field, a glaring data error in the system. This specific command allows the admin to hunt down the source of the crash. Using isNull scans the entire database to isolate the exact rows where a vendor code was never assigned. Once the missing data is identified, the admin might need to apply a fix to a very specific set of vendor accounts to get the products back online. To do this efficiently, the in operator allows the admin to check a column against a specific list of values all at once, rather than running a separate query for every single vendor code. Beyond just fetching items for a user, SQL serves as a diagnostic tool that allows developers to maintain the structural health of the database itself. Back on the screen, the result of these logical operations is clear, a curated list of exactly what you were looking for. Unprocessed data is just digital noise. Its utility depends on these logical filters to isolate the specific signals we actually need. A single tap on your screen triggers a request, passes through the logical gates of a where clause to discard the noise, and delivers a pristine result back to the interface. But so far, we have assumed all this information, the products, the prices, and the vendors, lives in one single organized table. What happens when the products and the vendors are stored in entirely different tables? This query shows the beginning of that solution, a process called a SQL join. We'll break that down in the next episode.